In this video, we'll discuss the most basic applications of homology theory. So let's just begin by reviewing what we've proved about homology theory. So for every space X, we have abelian groups HNX for all natural numbers n. And then this is functorial, so for every continuous map, homomorphism, we're calling F lower star from H star X to H star Y, from HNX to HNY for every n. And like I said, it's functorial, so that means that the map induced by the identity map is just the identity. And if we've got two composable maps like this, then G composed with F star is the same as G star composed with F star. Okay. And thirdly, this is homotopy invariant. So if got two maps, F0 and F1 from X to Y, now homotopic, then the induced maps on homology are the same. And key consequence of that, suppose F from X to Y is a homotopy equivalence. So what does that mean? It means we've got some G in the opposite direction. G composed with F homotopic to the identity on X, and F composed with G homotopic to the identity on Y. Then we look at firstly, we've got maps F star and G star between the homology groups, and G star composed with F star, well, that's the same as G composed with F star by this functoriality business here. Which is the G composed with F is homotopic to the identity, and by this homotopy invariance principle, that means that G composed with F lower star is the same as the identity star, but that's just the identity on the homology of X. And similarly, F star composed with G star is the identity on the homology groups of Y. So G star is inverse to F star, and F star is an isomorphism. Okay. So yeah, so this proves that if you've got homotopy equivalent spaces, then they have isomorphic homology. So in particular, if X is contractible, and contractible is equivalent to saying homotopy equivalent to a point, then we see that H star X is isomorphic to the homology point, i.e. H naught X is Z, hkx naught for k different from 0. Okay. Another point that's worth mentioning, if suppose only x is a homotopy retract, of y. So let's recall what that means. It means that we've got maps f and g as before, where g composed with f is going to be homotopic to the identity on x, but no condition on f composed with g. We still have this way hnx f lower star and g lower star hny with g star composed with f star being the identity. It follows from that f lower star is injective, g lower star is surjective. And hnx, you can also say hnx is a retract of hny. Okay, so those are our basic facts. Oh, and then let's also recall the homology of Sn. So Sn is homotopy equivalent to Rn plus 1 with 0 removed, so it's the same thing. So this was a free abelian group with 2 generators. It has a graded thing. So with An here lying in the 0th group and Bn in the nth group. So and so it's clear from this, well, if n is different from m, then homology of Sn is not isomorphic to the homology of Sm. Not isomorphic in terms of graded groups again. So if you look at if you just looked at combine all the groups together, then you just get a z squared. But the z extra generated in different dimensions. So as graded things, they're different, and so. So Sn is not homotopy equivalent to Sm, and also, of course, it's not contractible. And if it was contractible, you'd only have one z, but in fact, we've got 2. So no spheres are contractible, and spheres of different dimensions are never homotopy equivalent. And as a corollary of that, I want to claim that if n and m are different, then Rn is not homeomorphic. Let's suppose that f from Rn to Rm is a homeomorphism. Okay. And let's just put A is f of 0. Okay, so now we can consider this Rn with 0 removed. Well, let's start with Sn minus 1. And we've got this inclusion in Rn with 0 removed. So here implicitly, instead, I'm assuming that n is bigger than 0. I'll make an extra comment about the case n equals 0 at the end. Okay, so we've got the maps like this. So this is just the inclusion. Just write comments here. And then this is our given homeomorphism f. And then this one is just going to be x goes to x minus a. And then this one is going to be y goes to y divided by the norm of y. Normalization thing. And of course, we've got the inclusion map I in the opposite direction here, and also the normalization map R in the opposite direction there. Okay, so this map here is a homeomorphism. Okay, that's because f is a homeomorphism from Rn to Rm, and then you remove one point, it's still a homeomorphism. And then just translation here, this is obviously also a homomorphism. And we've discussed this before. These maps here are homotopy equivalences, as are these here. So our conclusion is that Sn minus 1 is to Sn minus 1, and therefore n equals n. Of course, r to the naught is just a point, and r to the n is infinite, n greater than naught, so Rn is so the case where n or m is 0 is kind of trivial. We actually use algebraic topology for the general case. So those are the most basic applications of homology theory. We'll do some slightly more advanced applications in the next video.